All right, you've made it to another module in the Forecast Builder training plan. This one tries to give you some background on the snow to liquid ratios that are used in the GFE and at least the NBM version 3. Now these will be changing with time uh, based on the use locally of consensus blends or NBM as the initialization scheme. But what this module tries to do is basically give you some background on how we got here and some of the liquid ratios that are used as science. We feel it's always good to know where you're going and know some of the background behind the science that's built into the system. So we're going to run through a few different things here. How do we get here? How were these snow to liquid ratios decided on and built? Some of those snow to liquid ratio techniques, a little bit of science, meat on the bone, if you will. And then finally, what some of the blend and NBM compositions are as of this recording. And again, those are going to change over the years, and this training will likely have to be updated. So with the more of a non-standardized approach that has been used in the GFE program across the CONUS since its inception, what we're trying to do scientifically as a community, I think, is trying to get more into a more uniform technique infrastructure where we're trying to remove and reduce the degrees of freedom that are in the system. So there was a national effort to consolidate the snow to liquid ratio techniques for the collaborative forecast process across our agency. And so some of the initial work was done in 2016 where SUs and ITOs came together to form a recommendations document after a science review, a recommendations document on what should be used for snow to liquid ratio in the GFE smart inits, and also give guidance to the National Blend Model developers at MDL. So this is right now the guidance document that we're using for the snow to liquid ratios. So let's move through a few different snow to liquid ratio techniques that are currently employed by the consensus blends and the NBM. Right now, as of this training, there's only three. That is the Cobb technique. There's the Air Force or max temperature aloft technique. That's can be referenced by either one of those names. And then also a thickness technique that uses the 700 to 850 millibar thickness. So let's jump into a few of those and just learn the background on some of those techniques. First, the Cobb technique. This has been used by the field for a number of years now. Dan Cobb and Jeff Waldstreicher came out with this technique in 2005. And it's really heavily weighted towards a vertical assessment in the model world, in the model sounding and environment. Looks at vertical motion and then also relates that vertical motion to the temperature regime for ice crystal growth. Remembering also that it keys on and bringing back to your memory that dendritic growth occurs when you have a good amount of vertical motion, basically leading to supersaturated conditions with respect to ice at that minus 15 regime, kind of in that minus 12 to minus 18 Celsius range. That gives you the best stellar dendrites, which is going to lead to very low snow ratios. So that's really what the Cobb technique keys on. And so for this example here, maximizes the snow ratio, as I mentioned, for high vertical velocity in the dendrite snow growth region. So on the right-hand side here, you see 12 and minus 18, the dendrite growth region is referenced. And then you see that the max vertical velocity plot over on the right-hand side with the maximum vertical velocity in that dendrite zone will give you a contribution in that layer of a high snow ratio. Now all the other layers are also assessed, and then an average snow ratio is determined for the sounding environment. So that's the Cobb technique, and because it's got some vertical motion relation, you will see some upslope footprint in terrain areas. So be aware of that with the use of the Cobb technique. Here's the second technique, otherwise known as the Air Force method or max T aloft method. What we're doing here is this technique looks for the maximum temperature in the lowest 500 millibars and then assigns a snow to liquid ratio based on that temperature and a equation relationship. And what I've done on the right-hand side here is just graph that snow to liquid ratio versus max temperature within the lowest 500 millibars of the troposphere here. And so you can see as the temperature, maximum temperature within the sounding profile decreases, your snow to liquid ratio increases. So the colder the profile, basically, the higher the snow to liquid ratio. So if we just take a sounding here and pick off a maximum temperature, here you can see just over freezing, about 0.5 Celsius. You match that up with the snow to liquid ratio curve and you get about an 8-to-1 liquid ratio. So as you warm to near freezing and have snow observed, you're really approaching zero with your snow to liquid ratio. Just a couple other examples. This is pretty straightforward stuff. Again, remember the overarching principle that as the temperature, maximum temperature aloft in your environment decreases, the snow to liquid ratio is going to increase. In this case, we have a very deep dendritic layer actually in this sounding, and we have a max T aloft of minus 12 Celsius, and the snow to liquid ratio does come out to 22-to-1, which is in that very small probability of occurrence climatologically, and can help the forecaster get into those higher snow to liquid ratios. In this case, I would actually expect something higher with such a deep and surface-based dendritic growth zone with such large vertical motion. This case could possibly give you in the area of 30 to 35-to-1 ratios. And so it's definitely a target that the forecaster can improve on if you see these types of environments present themselves. Finally, the third technique here is the thickness technique, and I, to be honest, wasn't as aware of this technique and actually the skill that it shows. And this is basically some research done by Brian Hurley back in 2005. And what I'm going to show you is some of this 850 to 700 millibar thickness to snow liquid ratio data that he had. It was based on 63 snow events in the mid-Atlantic states, and here are those events, and you can see that there is quite a weight towards the climatology here, which you'd expect right in that 8 to 10-to-1 snow liquid ratio regime. And most of these cases do not, in fact, none of them go over 18-to-1. So you have a small lower probability data set of those higher snow liquid ratios that get into the upper teens. So that's kind of the background on the 850 to 700 millibar thickness technique. But when Brian did this plot here of 850 to 700 millibar thickness and snow to liquid ratio for his event data set, there was quite a strong correlation coefficient of near 0.9. And you can see how it matches this linear trend line that we put on the graph. And so this line is represented by this equation, and so this technique simply takes and plugs in the thickness value for the 850 to 700 millibar layer, and the outcome is a snow to water liquid ratio. So it does add skill to the snow to liquid forecasts for the most probable snow to liquid ratios, and it can be applied to any model. One of the nice things you don't need is detailed vertical data that we have to have for the max temperature aloft and also the Cobb data set. You don't need those vertical sounding, all this vertical sounding information. You can basically use the thickness technique and achieve some fairly good skill for snow to liquid ratio. So finally, let's come to the last part of this small module here. We're going to talk about the consensus blends and NBM composition again as of this training. So here are some of the consensus blend snow ratio methods and for the given model that's in the blend on the left-hand side. So you can see a number of components here. In that technique, a 50-50 max T aloft and 50% Cobb output snow to liquid ratio technique is used. There was initial recommendations from the team that was put together to add the Rober technique, and that will be developed. It's in the works right now, some collaborative work between WPC and the MDL developers for NBM are looking to add the Rober technique, but that's not quite in there yet. So for those sound models that have sounding information that's high enough resolution, these two techniques are used in a 50-50 blend. And then for the ECMWF and the global model, that Cobb data set is we don't have enough vertical data to approximate the Cobb data. So what we're doing there is going to a max T aloft and 850 to 700 millibar thickness weighting there for the snow liquid ratio. And then again in the GFE, those are show up. There's a consensus short data set that has hourly snow ratio, and then the super blend data set is used in a 6-hour snow ratio block, and that's a time averaged block taken at the beginning and the end, possibly in the middle if that data set is there, and then just averaged basically the mean of that 6-hour period. What about the NBM, at least in version 3 and looks like 3.1, which will come out next winter? It will be this blend here that you see, and here's the NBM members, model members that are within that blend right now. There's also the GEFS mean sounding and the Canadian Global Mean Ensemble data set that we have. And again, much like the consensus blends, we saw the EC and the Canadian model, deterministic model, use the 50% of the max T aloft and the 50% 700 to 850 millibar thickness. These mean soundings do the same thing because we just don't have the vertical data that would be ideal for that. But the other deterministic models use a similar blend than that do the super blend and consensus data sets. So these should be in actuality fairly close in their snow to liquid ratio determinations or guidance, I guess I should use there. So here are some of those data sets. I'm just loading the snow ratio that's available from the national blend. You see the national blend goes out for different time lengths depending on which run it is through the period here, but you can see it's an hourly blend through the first roughly 36 to 48 hours, and then it moves over to a 3-hourly after that. Again, a quick mention that the NBM in version 3.2 will hopefully have that Rober technique added. Here's just a quick snapshot of one data set last year from 2016, mid-December 2016, giving you a feel for what the NBM snow to liquid ratio looks like. Certainly see a terrain footprint in here with some of the Intermountain region in the Sierra Nevadas, and then a stretch of higher ratio snows. So you can get some of these higher ratios within this blend in the NBM using the Cobb and max T aloft technique in the short term, first 48 hours or so. So you can see these higher numbers are above climatology for that area. So one thing to keep in mind, what can you as a forecaster do to improve the forecast? Always be on the lookout for these extreme snow to liquid ratios and make sure that the blends are accurately predicting those. And we're talking about the tail of the curve here. We're looking at extreme snow ratios of 25 to 1 or greater. These soundings typically have very deep dendritic growth zones, so keep your eyes open for this and ensure that your snow ratio is high enough for those outlier events. If you want more on that information, we can provide you with a PowerPoint slideshow, some of the work that Andy Just and myself and Dave Schmidt did here locally at the Weather Service in La Crosse. All right, so you made it through this module. If you want more information on the snow ratio team recommendations and that paper that I talked about that is being used as guidance, you can just go to this Google document and take a peek. Thanks for your attention.